So in this video, we're going to look at question E of question 3 in 2023 paper. So it says atmospheric pressure is due to the weight of the air above it. Yep, that is correct, I suppose. And then it gave us a diagram of a thin disk of atmosphere with a pressure difference due to the weight of the disk of air. Okay, and then, so first it says from the hydrostatic equation, pressure is equal to rho gh, we can trivially write down an expression for delta pressure. This contains both P and rho, so you need another equation to eliminate rho. Okay, from the ideal gas equation, obtain a relation between P, rho, R, T, and M. Okay, so these are questions under the first component. Okay, so let's see. Question E1. And then this is the first part of the first part of question E. So from the hydrostatic equation, pressure is rho gh, and then for delta P, let's write delta P first. So this should be delta P is essentially caused by the difference in the height, I suppose, because the only variable in this case would be h. So technically it should be delta P pressure should be equal to rho g delta h, or we can say rho g h2 minus h1, yeah, which was simplified calculations, I think. And then it contains both P and rho, so you need another equation to eliminate rho. Okay, so then I suppose we move on to the second part. From the ideal gas equation, obtain a relation between P and rho, R, T, and M, the molar mass. Okay, so let's write down the ideal gas equation first. So it just should be PV is equal to rho, nRT, yeah. So how do we tie things over here? The molar mass, okay. Obtain a relation between P and rho, okay. So, what we can say over here is that rho is density, which is m over v. And then we can somehow, okay, we can move it to the other side. So P should be equal to, let's see, so V will be equal to M over rho. So if we divide this to the other side, we will get rho N over M RT. And from this, okay, so we have the number of moles and mass. So suppose we can relate that to the molar mass. Okay, so the number of moles is the mass over the molar mass. So we can say that N over M should be equal to 1 over the molar mass. So the pressure should be equal to, this is rho over the molar mass, and then RT. And that should be the second equation. And then now using the hydrostatic equation, obtain an expression for dP over P in terms of mgh, r, and t. Okay. So, okay, so from the first equation, what we can say is that, okay, this is the third part. dp should be equal to rho g dh. And okay, so let's see, then it says dp over p, so then it should be rho g dh over p, which is rho over mrt. Okay, and then we can cancel out the rho, which leaves us with mg over rt dh, and then mgrt. I think none of these variables change with respect to the height. Yeah, so then the equation should be so dp over p should be equal to mgh over rt. Now then the last part says the temperature decreases linearly with height. In the form T is equal to, okay, so it's okay. So the temperature varies with height, and we cannot directly integrate the previous equation yet. So this should be just this expression. Like this. And yeah. So then the last part, it gave us the equation of temperature in relation to H. With this, use this with the previous result to produce an expression for atmospheric pressure as a function of altitude, okay? In terms of sea level pressure, P0G. The molar mass of air M, molar gas constants are, okay, so all of these are constants. And then the rate of decreased temperature with altitude, and blah blah blah. Humidity should not be considered. Okay, so it's basically just integrate the equation. And wait, it says, okay, so we have to integrate both sides. And so on the left side, what we have will be this should be long t, long p, and then it's from it is from P0, yeah, sea level pressure. And then on the right side, what we have over here is, let's see, we have mg, well, I can take out the constants first. Mg over r, and then we have dh over T0 minus alpha h. T0 minus alpha h. Okay, so then we can integrate this. So it is from 0 to h. Yes, and so if we integrate this, that should be ln, and then it's 1 over negative alpha. So, and then it's ln of T0 minus alpha h. Yeah, okay, and then h0, okay. So on the left side, we should have ln of p over p0. And on the right side, we should have mgr. And what we have inside should be minus 1 over alpha ln of okay, this minus that, so wait, it's technically, okay, I'm going to write this out first. So, and then it's minus, which is plus 1 over alpha ln of T0. So then this should be equal to, I'm going to factor out it first. So factor out alpha, alpha r, and what's left inside should be ln of t0 minus ln of t0 minus alpha h. So that should be ln of t0 over t0 minus alpha h. And I think what we can do here is, okay, we want to find the function of pressure in terms of height. So I'm going to do this. P over P0 should be equal to, we raise this entire thing to the power of mg over alpha r, and that should give us T0 over T0 minus alpha h, and then mg over alpha r. So then P should be equal to P0, and then T0 over T0 minus alpha h to the power of mg over alpha r. And that should be answer to the first part of the question. Okay, and then let's see the second part. So the second part asks, in a second flight, Charles ascended to 3,000 meters. Calculate the ambient temperature and pressure at this altitude. Okay, and then take the molar mass of air to be 0.029, and then molar gas constant, the rate of decrease in temperature, the reference, okay. And so, we want to calculate the ambient temperature and pressure. The ambient temperature and pressure at this altitude. There's two variables, however we only have one equation. Oh, okay. Two separate equations. So, okay, so let's first calculate the ambient temperature. So given in the question previously, T is equal to T0 minus alpha h. Now that should be a simple calculation. It's given that T0 is 288. Okay, so that should be 288 minus alpha. Alpha is the rate of decrease of temperature with height. That is 0.00976 multiplied by the height, which is 3,000, I believe. So then that should be equal to 288 minus 0.00976 multiplied by 3,000. Now that is 258.72 kelvins. Okay, and then we can calculate the pressure, which is just subbing values. Okay, so we can just say, I'm just going to put this entire thing into the calculator. So, this should be P0. Okay, so P0 is 1.01 10 to the 5 multiplied by T0 over T0. Okay, so wait, T0 minus alpha h, that's just, okay, so it's just 288 over what we calculated previously. So 258.72, and then it's raised to the power of mg over alpha r. Okay, so m is 0.029, and then multiplied by g 9.81 over, this should be alpha r. So alpha is 0.00976 multiplied by the molar gas constant, which is 8.31. Yeah, so then the pressure at 3,000 meters should be, that is 1.47, I would say, 471 times 10 to the power of 5, and then should be in pascals. Yeah, and that is the answer to the question. So let's move on to the third part. So third part says the balloon expands in volume by 30% at a height of 3,000 meters. Calculate the pressure inside the balloon assuming no hydrogen has been lost. Determine the stress in the skin of the balloon. Estimate the Young's modulus of the composite skin material. Okay, so this is interesting. So the balloon expands volume by 30%. And then I suppose we can use ideal gas equation upon that. And then the first one is calculate the pressure inside the balloon, assuming no hydrogen has been lost. We aren't given any initial values in this specific component of the question. So can we utilize the second part? I think we can, yeah. So, okay, so we can just directly use the pressure from the second part of the question. Wait, calculate the pressure inside the balloon. Well, I suppose the pressure inside the balloon is just the pressure of air outside of the balloon. Yeah, because the pressure has to be balanced out in order for the balloon to remain as inflated. So then we can say the pressure is just equal to 1.471 times 10 to the 5 pascals. Now let's see. The second part, determine the stress in the skin of the balloon. Okay. So it says determine the stress in the skin of the balloon. Now the stress, let's just say S, is equal to the force over area. Yeah, the force over area. So technically the internal pressure, something like that. Now in this case, the pressure of the skin material, let's say, right? In the skin of the balloon. Okay, so it said the pressure in the skin of the balloon. Okay, so what I'm thinking of right now is that we have the skin of the balloon, something like this. We have pressure from the outside, right? And then we have pressure from the inside that essentially balances out with each other. And then we want to calculate the stress within this skin of the balloon. Now, do we add two pressures together or just one of them? Well, I suppose in this case, let's think about normal forces. Okay, so about normal forces, what you can say is that in order for the skin not to break or anything similar, it has to provide the same normal force toward that way, the same normal force towards that way as well. So technically it's in two completely different directions, so it's two independent forces, so we should add them together. Yeah, okay, so then the stress of the balloon should be 2 times the pressure. Okay, so then that should be 1.471 times 2, which is 2.942 times 10 to the 5 pascals. No, technically not pascals, but in terms of units, it is. I suppose it's more accurate if we say Newton per square meter. Now the last part. The last part simply just want to calculate the Young's modulus of the composite skin material. Now I suppose that will be so the Young's modulus, let's say E, will be equal to the stress and then multiplied by the reciprocal of the strain. Now the reciprocal of the strain is just L over X, the initial length over the extension. So I think what we can extract this information is from the idea that the volume was expanded by 30%. So how do we relate this to the initial? Okay. So I think what we can say is that we assume the balloon is a perfect sphere. And then it essentially increases by 1.3 times, 30%. And I suppose what we can say is that the balloon is something like this. It's like a hollow sphere, and then when it expands, the volume will stay the same. However, the thickness will decrease. So I think we can calculate the decrease of the thickness, and then we divide it by the initial thickness. Okay, so how do we approach this? Let's see. Well, calculating this accurately would be rather tedious. So I think one assumption that we can take is that the skin is very thin in comparison to the volume of the balloon. Then we can say is that the volume is simply just the area, which is 4 pi r squared multiplied by the thickness. Sorry, the volume. So the volume is equal to this. The volume remains constant, and then the volume of the skin of the balloon remains constant. And then the volume balloon increases by 30%. Okay, and then we can relate that to the radius, and then we can solve for a kind of like a ratio between the thickness. And yeah, I think that will work. Okay, so let's see, how do we do this? Initially what we have is let's say Vs for the volume of the skin. We have 4 pi r squared times the t. Now then, what happens is that the volume increases by 30%. So the volume of a perfect sphere is 4 over 3 pi r cubed. And then if the volume increases by 1.3, then essentially what we can say is that the r is essentially increased by the cube root of 1.3. So yeah, so then how do we relate this? Now then, the change in thickness. Okay, so V in this case we assume is 4 pi r squared times the thickness. So what we have over here is that the volume remains constant, yeah? So 4 pi r squared times t, and then we have t prime. So, and then we have 4 pi, we can cancel out the 4 pi r squared, and then this is multiplied by the extra factor, which should be 1.3 to the power of 2 over 3, as it is r squared. So we can cancel out 4 pi r squared, and what's left will be t prime is equal to t over 1.3 and then to the power of 2 over 3. Okay, so then we calculated the new t in terms of the initial t. So then we can calculate the strain. So we can say basically technically we're calculating the reciprocal of strain. So that should be the initial one is t, and then the change in the thickness is just t, and then it should be technically decrease. So therefore it's 1 minus 1.3 to the power of 2 over 3. And no, this is 1 over 1.3 to the power of 2 over 3. So we cancel out the t's, and then we can plug this into the equation. So the Young's modulus of the skin will be 2.942, yeah, times 10 to the 5 multiplied by 1 over 1 minus 1 over 1.3 to the power of 2 over 3. And then we plug this into the calculator to get the final answer. So 942,952. And then multiply by 1 over. This is 1 minus 1 over 1.3 to the power of 2 over 3. No, that is 1.83 times 10 to the power of 6. 10 to the power of 6. And that will be the answer to the question.